All right. The number of basic types of reaction is 3. Do you guys want to go through this? Yeah? No? Yes?
I just wanted to go through one of the reactions.
Okay, we'll do that. We'll just quickly go through. What are the 3 basic types? Metathesis, redox, and acid-base. Combustion is an example of a redox. Formation of a precipitate or a gas is the driving force for redox reactions. Formation of a gas can help, but it's not enough. It's not enough because the energies involved. Formation of a gas is going to be an increase in entropy. An increase in entropy is always going to help. However, countering that is these large changes in energy when you change oxidation states. So, for example, sodium metal versus sodium ion. There's a huge difference in that. And so, formation of a precipitate or gas is just not enough for redox reactions because they're much larger change in energies due to the change in the oxidation state. However, in metathesis and acid-base, there's no change in oxidation state. And so you're just looking at the bonds there. Single replacement is a redox reaction, which is double replacement is what? Metathesis again. Which is a stronger acid? Well, both of these are in water, so it's a leveling effect. Leveling effect question. Which is the strongest oxidizer? Below? It would be nitric acid or nitrate and H+. We don't have to have the ratios, here. So, for example, the ratio on the redox charts, 1 nitrate to 4 H pluses. We don't have to have that, but we would need 4 nitric acids, and 3 of the nitrates would be speculators. Over here, fluoride. Fluoride's a reducer, not an oxidizer. Hydrogen peroxide can go either way. Oxygen's -1, so it can gain an electron to go to -2, or it can lose an electron to just go to O0 or O2. And so hydrogen peroxide is an interesting one, but it can go either way, but not with equal ability. It's much better oxidizer than it is a reducer. Which one's a stronger base? The bases we want negative charge density in a lone pair. This is better, nitrogen. Fluorine does have negative. Each fluorine's -1, but it's not good at sharing. So this for sure is a better base. In fact, this isn't even considered a base. B is nitrogen trifluoride. We wouldn't consider that a mean at all, right? Nitrate is considered electron poor. Nitrogen's +5. It's max positive oxidation state. Here, ammonia, it's -3. It's max negative oxidation state, which is electron rich. Ammonia. Which is a stronger Lewis base. Now, Lewis bases, we can't use the chart. Bronsted, which is a stronger Bronsted base? Which one would be a stronger Bronsted base? Oxide. Why did you pick oxide? Higher charge density. Good. Smaller size, same charge. For Lewis acid-base reactions, we have to use HSAB. Does anybody remember what HSAB stands for? Hard soft acid base. Right? And we got to match it because we're forming MOs. So we want good atomic orbital mixing for those. So get that. An aqueous solution of 1 molar sulfide cannot be made. That's true. Why? I'm sorry? It hydrolyzes 100%. It's a strong base. All strong bases hydrolyze 100% in water. All strong acids hydrolyze or ionize 100% in strong acids. And this is just strong electrolyte. Sulfide is a strong electrolyte, so it's not going to exist. The hydrolysis reaction we're actually going to look at in depth in Chem 1B. There is a minute quantity of sulfide that can exist, but 99.99999, etc. percent of the sulfide reacts and hydrolyzes. A redox property of ammonia is that it would be an electron-rich reducer and potentially flammable. That is true. So we should be able to burn ammonia. What is the oxidation state of chlorine in bleach? Yeah, +1. This is why we never mix bleach with ammonia cleaners. Somebody died recently, apparently. I'm not exactly sure if this is correct, but this is somebody reported this in the news at Buffalo Wild Wings. The manager there mixed ammonia cleaner with a bleach cleaner to clean the floor, generating toxic oxides of nitrogen, and ended up dying, unfortunately. But +1 for chlorine means it's electron poor. This one, this is what Werner won the Nobel Prize for. This is not really the way we should write this formula. What is the way we should write this formula? Down here, it should be the pentamine, chlorido, cobalt, 3 chloride. So, well, this was the big mystery. The observation, what was predicted was this should precipitate out 3 moles of silver chloride, but it only precipitated out 2, so it was a big mystery. And so the person who came up with the hypothesis, this was observation, and the person came up with the hypothesis why only 2, and it was reproduced. It was Werner, who proposed an entirely different structure. This entirely different structure, he was the first to propose this idea of complexes, complex structures, and so that's why cobalt has a coordination number of 6. Amines are better base than Lewis base than chloride, and so the amines will preferentially bond to the cobalt and create this kind of structure. And so one of these chlorides is actually covalently bonded. 2 of these chlorides is ionically bonded. That could have been another multiple choice question, Are all 3 chlorides ionically bonded here? No. 2, well, how many are covalently bonded? How many are ionically bonded? That kind of stuff.
Are there other compounds that have
Yes. Yeah, there are.
do
You don't memorize them. The only reason this one came up is because I talked about it in class, and so otherwise I wouldn't have thrown out a question like this out of the blue. This is one of the ones that we were looking at for silver chloride precipitation. It's easy to forget, because it was a long time ago, but that's it. And so there are lots of compounds. You don't have to memorize them, basically. But this is the one that was used to illustrate Werner and his Nobel Prize, so this is why I chose it. CF4 is an electron-rich and flammable compound. No, CF4 does not burn, right? You can't burn it. Why? Yeah, carbon's already in +4, so CF4 is non-flammable. In fact, people want to get rid of CF4 and the other. It used to be at one time these fluorocarbons and chlorofluorocarbons were thought to be inert, non-toxic. CF4 is non-toxic. You don't have to worry about dying. But even though it's non-toxic, apparently a lot of these forever compounds have other effects on hormones and whatnot, and so things like polyfluorinated compounds are seeing extra attention nowadays. For the health effects, not necessarily ozone. CF4 will impact the ozone layer as well, but human health effects. What is the coordination number of lead in this one. Here you'd have to memorize EDTA is a hexadentate ligand. We only had 3 polydentate ligands that we saw in the book. And that was EDTA, ethylene diamine, and oxalate. So, what is the coordination number of this? I screwed this up. Do you see my error? This cannot be neutral, because that would mean chromium would have to be in the +6. It's unlikely to be in the +6 in this kind of thing. So this is supposed to be 3 minus. Just screwed up the charge on that. But anyway, you should still be able to answer it. It should be 6. All right, this is where I talked about other ligands, analogs like methylene diamine. And methylene diamine, you just have to know this one.
It's right. I remember 16. Well, 17.
Oh, what was that?
Sorry.
Okay.
There's 2 number 16.
Oh, yeah, I screwed it up. Sorry. On the key, I think on this one I fixed it. I don't know. But you're right, the numbers are screwed up. How about propylene diamine or butylene diamine? Would those be bidentate? Yeah. So this is just the number membered ring here. All right, and then we had the nomenclature. This one, you could either write carbonyl or the, actually no, this one you can only write carbonyl. NO is the weird one. What do we call NO? Nitrosyl, which is a lot easier to remember. No, it's, yeah, oxidonitrogen. All right. So the first one's metathesis. Here we had 2 driving forces. Some people wrote both, so I get, and some people wrote 1. All you need is 1, and I mentioned that, but if somebody wrote both, then I gave them full, and then if somebody wrote 1, I just took off just a small amount. Yeah. The other thing was H2SO4. A lot of people ended up splitting H2SO4 into 2 H pluses and sulfate. That happens every year, but if that's the case, then it changes B. If we could split up HSO4 minus, then we would get 2 strong acids. We have H2SO4, which is strong acid, and loses its proton, and then if you take out the H plus off HSO4 minus, that makes this a strong acid. So we get 2 strong acid protons. But in reality, if I look at sodium bisulfate, is sodium bisulfate considered a strong acid? No. Sodium bisulfate, that's considered amphoteric. This is an acid and base. Its base properties are so weak, we don't really consider it base. So I should have put a little asterisk there on the base. It's really just an acid. It's like the base strength is like chloride, or nitrate. Things we don't even consider basic. A lot of people wrote thiosulfate. Thiosulfate is S2O3 2 minus, and so just to mix up with this. This turned out to be an acid-base reaction. Some people did redox, which is fine, but there's no redox reaction. At least there's no driving force for redox reaction here. And which was the number, Colin, that you had?
It was the
D. Sodium metal and potassium iodide. A lot of people did single replacement for this. But you have to be aware, if you use single replacement, you have to be aware of all the exceptions to single replacement. This would have been one of the exceptions for single replacement. All right, this one.
Yeah, I was just wondering that how you would set it up with the products. So since there was chromium and iodide in both of the products, and then I wasn't sure where the hydrogen peroxide would go.
Yeah, whenever we have hydrogen and oxygen, this is a trick. The only reason I did this way is because the book had it, I think, like this. And so this is an advanced problem. But I figured this is from chapter 5. So it's Chem 1A. But now we're in Chem 1B, so it's probably all right. But basically, if this were a standard problem, there'd be one more product here. It'd be plus water. But the situation with water is we balance it anyway. We add water here and there. It doesn't really matter. And so whenever we have a compound that contains hydrogen and oxygen, it's always going to go to water, because when we balance out the oxygens, we got to add waters for each O. And so it makes it harder, but in a sense, it's not harder. If it just is missing, so you have to do an extra step, and that's the situation you find for a lot of advanced problems. A lot of advanced problems, you have to do an extra step, so they don't do it for you. You have to do it yourself, and it makes it difficult sometimes. But and this is why the more you see, the better, because then you can see such things as this. And so here, hydrogen and oxygen, I didn't really care, because we got to balance it by adding waters. And so there must be water. And then there's plenty of water. These are all aqueous, so there's plenty of water present anyway. So we could have water as a reactant, we could have water as a product. Now, some people tried to split it up, so they took the chromium. Now, this is tricky, because you think chromium 3 iodide is a strong electrolyte, so it should split up, And so, what are we going to have here? Now, the interesting thing about this is when we have redox, we have the 2 half reactions. One is called the reduction half reaction, the other is the oxidation half reaction. So this is another advanced level. When you see chromium 3 iodide, is that electron rich or electron poor? And so when I see chromium 3 iodide, well, I see the chromium could go either way, it's +3, but when I see iodide, immediately what comes to mind? What comes to mind for iodide is it's a good reducing agent. Iodide is I- and this is jumbo. And so if you have a big iodide is a great reducer. And so I see a strong reducer here. But then when I look at the products, what happened to the iodide? The iodide got oxidized all the way to periodate. And then I look at what happened to the chromium. Chromium could have gone either way. It's +3. But what way did it go? It got oxidized. So this is interesting. Both the chromium got oxidized to the max. The max is +6, and the iodide got oxidized to the max. The max on iodide is +7. And so you need a powerful oxidizer to do that, and we have a powerful oxidizer. The powerful oxidizer in this case is hydrogen peroxide. So we're using hydrogen peroxide as a strong oxidizer, and we're going to oxidize the heck out of this thing. And so some people split this up. They tried to make the chromium become oxidized, and the iodide, they were looking at all kinds. So some people added in one more product here, a new product, iodine, and it kind of makes sense to split it up that way. But when I look at this, I automatically see that hydrogen peroxide oxidized this whole thing completely. I mean, you can't get it more oxidized than this. And so this is what you want to do. This is why when I look at these types of things, I always look at it at the oxidation states first. You know, I don't like memorize the chart or do that kind of stuff. I just look at the oxidation states and see what I expect or how they should behave. You know, so it's not that I memorize that, but I can easily see that this thing got oxidized to the max. What oxidized it? This. And so first, this gets converted into these two, complete oxidation. Now, for the driving force, oh, did I? I ran out of room here, so I moved it over here. All skeleton redox have driving force, you know. Otherwise, we wouldn't get these products. So this is one of these situations where you aren't sure if you could oxidize it to the max. Maybe hydrogen peroxide could oxidize the iodide, but might have difficulty oxidizing the chromium, you know. Or maybe it has trouble oxidizing both. Maybe we don't oxidize it to periodate. Maybe we just oxidize it to iodate or hypoiodite, or iodite. You know. And so depending on the conditions, well, the conditions must be severe here. You know, we could have mild conditions, and that's often done, and that gives you partial oxidation under mild conditions. And so whenever we have this, it's this. There's got to be a driving force present, so we know it's going to go strong, strong, weak, weak. I didn't talk much about this at all. It's more kind of review. All right, so that's the test there. All right, we're going to go back to chapter 13 here. And so we left off talking about delta H. You know, what we want to know is, can you tell me all the ways to determine delta H? One, we could do it experimentally using calorimetry, you know, et cetera, et cetera. Like delta H, can you tell me all the ways to determine delta H? Can you tell me all the ways to determine delta U? Delta H we could get from coffee cup calorimetry. Delta U we can get from bomb calorimetry, et cetera, et cetera. And so that kind of stuff. Okay, then we wanted to do the same thing. We wanted to go over to delta S and figure out all the ways that we can determine delta S. And so one of the ways, which I labeled the easiest, is just to take the entropy final minus the entropy initial. You know, the sum of the entropies of the product minus the sum of the entropies of the reactants, something like that. But what are the other ways that we can determine what delta S is? And so let's talk about some of the other ways that I don't remember how I had this set up. We talked about delta S of phase transition, did we?
Yeah.
Okay, that's one. And that comes from delta S can be related to the heat exchange under reversible at a given temperature. Okay, and then we can come up with some other things here. Let's see. um, based on this. And I'm not going to go through the derivation. The derivation is in your book, and let's take a look at it. This book is actually pretty good book.
So just to clarify, one of the ways is if we want to find the delta S associated with the phase change, it's the delta H of the phase change over the temperature plus the phase change.
Yes. Yeah. All right, when we have a phase change, the temperature is constant. And so let's take a look at some other scenarios for calculating delta S. Let's see if I can get the page change here. All right, this is delta S of a phase change or transition. And this is going to be like the boiling point, the melting point, or the transition temperature. And this is just delta H of the transition. That is delta H of vaporization, delta H of fusion, et cetera, et cetera. We also have these equations here, and that is delta S. Okay, this is heating or cooling at constant pressure. And we're assuming that the heat capacity at constant pressure is constant over that temperature range. And the heat capacities can change. You know, this is the whole point of the measuring the heat capacities over a temperature range to relate those to entropy, and we can get the absolute entropies. You know, when we have delta S is S final minus S initial. If we have S initial as 0, that is using the third law, then we can get S final. But this is calculating delta S. So here's where we would use the heat capacities. The heat capacities are found in Appendix D. So let's say I want to figure out what is the entropy change of warming up water. You know, obviously hot water is going to have a higher entropy than cold water. And so we want to find that out. But when we look at Appendix D, what is the entropy that we see? The entropy that we see in Appendix D is the entropy of water at 290 room temperature. And so what if we wanted to know the entropy change of warming that water from 298 to 373? You know, what would the entropy change there? And so using some calculus, and the delta S is related Q reversible over T, we can derive this equation. We're not going to use calculus, and we're not going to derive this equation, but this book goes through, and other books go through the derivation of this. So if you do take an advanced class where you need to know the derivations, you know, this is some calculus type stuff here. Although this isn't full bore. If you look in other books, they'll get into the calculus. Like, they'll just briefly talk about it here, and taking this kind of stuff. We're not going to do that. We're just going to look at the end result. We just want to be able to use that. So this gives us another way of calculating delta S. We can see, does delta S increase or does delta S decrease? We want delta S to increase for spontaneous processes. This is another one here. This is a change in state, temperature and pressure, initial and temperature. So we change the temperature, the pressure can increase. This is going to be for constant volume. The looks like. Right. There. That's what it looks like, but anyway, temperature and pressure. So here, if you're doing something like this, we could do this. There. So we just add up the entropy. This is the entropy that's due to the temperature change, which is the same equation here. And this is the entropy that's due to the pressure change. Now, why is it negative? We should just add the two entropies. And one of the things the book likes to do that I don't like to do is they like to flip this. If they flip this ratio here, then they can change the sign over here, right? And so they like to put the final on the top and the initial on the bottom, but for pressures, it's the initial on the top and the final on the bottom, and then this is positive. And so that's another equation. So we could use these equations to do some additional delta S. We aren't really going to use these much. You know, I think I assigned one homework problem or two homework problems with this. Just as an example, primarily the way we're going to calculate delta S is by using Appendix D. And we're just going to do the reaction under constant pressure and 298 Kelvin. Okay. Now, if we do increase the temperature, then we want to use that other equation there. Or if we do an increase, we want to use this equation here, and that is volume and pressure are directly proportional or inversely proportional. So if we increase the volume, what happens to the pressure? It goes down. So they're inversely proportional. And so one thing we can do is delta S is equal to this, you know, if I flip this over here, which would be NR ln. And so we can come up with an equivalent equation for volume. And so from the book, we have the temperature, delta S, and temperature, delta, and change. And we have delta S and a temperature and pressure change. Then we could have delta S and a pressure change and leave the temperature the same, and we just use the second term in that. And so delta S is going to equal here. We'll just change the sign of the second term here, NR ln, and we're going to flip it here. And so NR ln, and then we're going to flip it, and so it's going to be P initial over P final. Or we could flip this and call it negative. Now, we're going to come up with one other equation, delta S and volume change. We keep everything else constant. It's supposed to be volume. So it's just going to be the same thing. It's going to be NR ln V final over V initial. If we have a volume change, we can calculate. So let's say the pressure stays the same, the temperature stays the same. So what is the entropy associated with this? Now, this is for ideal gas over here. And for an ideal gas, this is what we call isothermal. You know, delta S and volume change. This is isothermal. Let's say the volume increased. If the volume increases, is any work done? Well, it's like blowing up a balloon. If you blow up a balloon, does it cost energy or? Yeah, it's going to cost energy, so work is done. Now, if the temperature is at 298 Kelvin, and the temperature here is at 298 Kelvin, was any energy lost or gained? In other words, where did the energy come from to do the work? And so normally when we do work is minus P delta V. You know. It's negative because the system loses energy doing the work if the volume expansion is positive. And so what we do is this. This is our normal way we calculate the work. And so basically, if it's isothermal, all that work is coming from heat from the surroundings, you know, because this should get cold. Have you ever had one of those compressed gas in a can to blow off the keyboards and stuff? And have you ever felt how cold that can gets? The can's getting cold because a lot of work is being done. The gas is expanding. It was compressed in a small volume, now it's expanded into a large volume. So work is done. And where did the energy come from? The energy is going to come from your hand. Your hand's going to get cold because it's going to cost energy. And so that turns out to be the heat. And so delta S is going to be the energy available for the work, which is going to be equal to the heat. And so basically where this equation comes from, this N R ln V final V initial comes from this. It comes from calculus. What we do is we do infinitesimally small changes, and we do this reversibly. And so the volume change is infinitesimally small. And so this work comes out like this. And so we have infinitesimally small volume changes. And so the equation comes out a little bit different. So this is the work or the heat. You know, the heat, we're going to lose heat. The surroundings are going to lose. You know, the system gains to maintain the same pressure or heat in this case. And so that's kind of where this equation comes from. It's the work that's involved in expanding the gas using calculus and infinitesimally small changes. Okay. And so we're not actually going to do this kind of derivation. Normally when we calculate work, we just use this here. All right, so these are some more ways to calculate delta S. This is in the book. And then, of course, we had the Boltzmann equation, too. Delta S is equal to K, the Boltzmann constant. So we'll call it KB, ln of W. That's another way we can calculate it. Now we want to do the same thing for delta G. We want to know what are all the ways we can calculate delta G. Well, the easiest way is if we restrict the conditions. And so the easiest way to calculate delta G is if we do this under standard conditions at 298 Kelvin, then it's super easy. Because here we can get delta H naught from appendix D minus T delta S naught at 298 Kelvin. That's the easiest. But this means we must be under standard conditions, and we must have a temperature of 298 Kelvin. Well, the first scenario comes, what if I don't want 298 Kelvin? And so the first one would be delta G standard at temperatures other than 298. Well, the best obviously, is if we have the delta H and the delta S at that temperature. But we don't often have that. And so what we'll do is we'll just make an assumption. If we don't have this data, then what we can say is the next best. The next best option is just to estimate the delta G. We're going to estimate it by using the delta H of 298 under standard conditions minus T delta S under standard conditions. But the problem is this. What if we are not at standard conditions? What if I want this to be at, let's say, not 1 molar, but I want to use 6 molar? Or I want to use 12 molar? Or I want to use 16 molar? What am I going to do? And also, the standard conditions is really weird. Think about the standard conditions. Standard conditions means what? Pressure is 1 bar. Solutions are all 1 molar. So if we look at a reaction, and I want to do this reaction under standard conditions, so I'm going to do standard initial conditions. So this is a solution. What's the concentration have to be? 1 molar. Now the HCl is under standard conditions. And the NaOH has to be at 1 molar. And what about the sodium chloride? Should I make the sodium chloride 0 molar? Is that okay? Is 0 molar okay for standard conditions? No, the sodium chloride has to be 1 molar. Who wants to do a reaction under standard conditions? Because if I did this reaction under standard conditions, then I'd have to mix up the HCl, I'd have to mix up the NaOH, and I'd have to mix up the NaCl. Now the water is weird because this is pure water. And so how can you have 1 molar water in pure water? Kind of thing, or close to pure. I shouldn't say pure, it's close to pure, because water is a solvent. And so if somebody says, okay, go ahead and mix me up a 0.1 molar water solution in water. Does that make sense? It doesn't make sense. And so water, being a pure liquid, we say has an activity, unit activity. Its activity is 1, so we ignore it here. And so pure liquids and pure solids are pure. Their concentration doesn't change in that sense, and therefore their activity does not change.
I have a question.
Okay.
If you have 1 molar HCl and 1 molar NaOH, and then you react them, wouldn't you just get 1 molar NaCl stored in that?
You would, but the driving force would be different, because that would be called non-standard conditions. We have the driving force for standard conditions. The driving force for standard conditions requires this. This makes no sense at all. This is a hassle. We're trying to make sodium chloride. And so you're trying to make sodium chloride, you have to pour sodium chloride into the mixture. It doesn't make sense. We're trying to neutralize this, but ultimately we're making sodium chloride. So if we do this under standard conditions, this is our driving force here. This is our delta G under standard conditions. If we do this at 290 Kelvin, then it's fine. But this would be non-standard. initial. The non-standard initial is 1 molar, and 0 molar. Who wants to put product in there to begin with? So this is non-standard. So can I use delta G standard for non-standard conditions? No, I can't. The temperature could be the same, 298 Kelvin, no big deal. But now this is no longer standard. So number one, the weird thing about standard conditions is everything has to be at 1 molar and everything has to be at 1 bar. And then we look at the driving force. Well, we're in luck because what do you think? If I have product here to begin with, the driving force isn't going to be as strong. If there's no product here, the driving force, so I expect this driving force to be bigger, more negative than this driving force. But we have to do it this way. Otherwise, how many tables do you want? You know, this would be too horrendous because we'd have to have delta H, delta S under all. Like, for example, maybe I don't start 1 molar, maybe I don't start 0 molar, maybe I start off with a 1/2 molar here, you know? What is it going to be? And so it's just too much. So having it under standard conditions means appendix D is not out of control. You know. But we want to know how to handle non-standard conditions. Need to. And so I'm not going to go through the derivation of this equation. What we're going to do is we're going to take our delta G. Okay, so we're going to go non-standard now. Delta G non-standard at 298 Kelvin. So we don't want to go too crazy. So we're going to keep the temperature at 298 and try to make our life as easy as possible before changing the temperature, because we're going to do delta G non-standard at a temperature not equal to 298 as well. And so if we go delta G non-standard at 298, then delta G non-standard at 298 is going to equal delta G standard at 298. And then what we're going to do is we're going to correct this. You know, in other words, having more product will mean the driving force isn't going to be as strong. Having less product means the driving force should be stronger, right? And so what we're going to do is we're going to adjust the driving force depending on the ratio that we start off with, you know, whether it's a greater ratio than 1 or a lower ratio than 1. And so what we're going to do is we're going to do this. It's going to be a delta G under standard conditions plus RT ln of Q. So, or minus, RT ln of Q. This is where Q is defined as the reaction quotient. Reaction quotient. And what the reaction quotient is, it's the activity, what we call the activity of the products initial, or what you're given, over the activity of the reactants initial. Dot, dot, dot. So what is the activity? The activity is this. The activity of a solution is approximately equal to the molar concentration, its ideal concentration. Now, it's going to deviate as the solution becomes less and less ideal. It starts to deviate. And so this is better at low concentrations than at high concentrations. And the same thing with the gas. The activity of a gas is just going to be approximately equal to its partial pressure of the gas. The activity of a solid is just one. Its concentration doesn't change. It's 100% solid. So if you have half a pound of gold versus a pound of gold, its concentration shouldn't change. The same thing with liquid. If you have a half cup of water versus a full cup of water, it's still pure water. Hopefully pure. And so
What's the solution?
the molar concentration. The square brackets means molar concentration. This is the pressure of the gas. So the units here are molarity. The units for the pressure of the gas are in bar. The reaction quotient, reaction quotients are actually dimensionless. Activities have no dimensions. Dimensionless. No units.
Oh, good.
So Q has no units. No, K is the same. You know, K EQ. This is the equilibrium constant under thermodynamic conditions. Is equal to activity of the products. So GG, HH. Well, it looks exactly the same. What's the difference between K and Q? Well, Q's initial, K is at equilibrium. And so Q and K are the same thing if they're both at equilibrium.
You have Q at equilibrium if it's just initially.
Yeah, if the initial conditions are at equilibrium, then Q initial is equal to Q equilibrium. And then we have all the variations. We have QC, QP. You know, QC is all solutions, liquid or gas solutions. QP is just gases. We have KC, KP, etc. So variations of this. We're not going through the derivation of this, but it kind of makes sense. We take this and we adjust it. So the more product we have, the more positive this becomes, right? The more product we have, then ln is going to be greater than 1, which is positive. And this is going to make this whole thing more positive. And if this thing becomes more positive, that means the driving force goes down or driving force goes up. The more positive the delta G, the less favorable, the less the driving force, right? We want negative delta G. The more negative this is, the better. And so if we take a ln of a fraction, that is, if we have more reactant than product, there's going to be less than 1. It's going to be some fraction. This whole thing is going to go negative, and that's going to make this whole thing more negative. And so do you see how that works for this? And so this is one way of remembering that this is positive. And so all we need to do is just plug in the initial activities here. We know what R is. R is just the gas constant, 8.3145 joules per mole Kelvin, and T is just the temperature. And so we can calculate delta G Okay, that's at delta G at 298. Now let's look at delta G at 298 Kelvin. And it's at equilibrium. So if delta G is at equilibrium, then that means delta G at 298 Kelvin has no driving force, essentially. I mean, one way or the other. And so delta G is equal to 0. So it's just, it's a dynamic equilibrium, so the reaction is still going, but the forward and reverse rate are equivalent. And so this is going to give us delta G naught at 298 Kelvin plus RT ln of Q. Now, if we're at equilibrium, then these are not initial. Well, they're initial and they're equilibrium. And so if the activities are all at equilibrium, then Q is just equal to K at equilibrium. And so this is 0 is just going to equal delta G naught at 298 K plus RT ln of K. And so this gives us another way of calculating delta G naught. Not delta G, but delta G naught. And so we could calculate delta G naught because it's just going to equal minus RT ln of K. And so we need to add this to our ways of calculating delta G naught at 298. Okay. And what this is this. Let's see, delta G naught at 298 K, which is equal to minus RT ln of K. And so what we want to do is we want to get an idea of the relationship between K and delta G naught. And so let's take a look at the relationship a little bit more in depth here. Jump to the page. So this gives us some numbers. The more negative, the bigger the driving force. So minus 200 is a large driving force. But conceptually, what does that mean, a large driving force? What it means is if we look at the equilibrium constant, the equilibrium constant is going to be proportional to the products over the reactants. So minus 200 means the ratio of product to reactant is like 10 to the 35. 10 to the 35 parts of product to 1 part reactant. And so this is saying it's going to be nearly 100% reaction. And so if we have like a minus 200, there's so little reactant left over. It's practically 100%. Even if we go to minus 100 kilojoules, a minus 100 kilojoules is still like 10 to the 17 parts product to 1 part reactant, right? This is crude because the exponential term can change how we interpret these numbers, but nonetheless. It's not until we get to like minus 10. Minus 10 is not all that strong, so that's 56 to 1. 56 to 1, that means there's lots of product and lots of reactant at equilibrium. And so we can use Chem 1b stoichiometry for all these, right, because we know the ratio. But for Chem 1a stoichiometry, we only do that at the limits, like here. Chem 1a stoichiometry, like minus 100, minus 200, fine. We'll just say 100% reaction. Or here, plus 100, plus 200, 0% reaction. But if we want a more accurate, then we do equilibrium. It says equilibrium calculation is necessary here. No, it's necessary, I'd say from 50 to minus 50, it's necessary. Not just here. But you could do equilibrium calculations for the entire spectrum, and that's what we're going to do. We don't care, you know, if it's at the extremes. We're still going to do equilibrium calculations, and even if we get a tiny, minute amount of reactant or product left over, it doesn't matter to us. We're still going to do it. Okay, so this table gives us an idea of how the driving force is related to the ratio product to reactant here. So I'm going to remember that.
Is it possible to ever have like actually exactly 100% product?
And at the limit, K would have to be infinity to have all product, and K would have to be 0. Or, yeah, 0. And so, we could, you know, if you have a finite number and it's enclosed in a container, then you could have 0 reactants because you just don't have enough population to have one of those, you know, by chance, you know. All right. Likewise, this gives us another way of determining K. One way of determining K is by experiment. You know, you just measure like we did. You know, we took 3 experiments and then took the average K value from the experimental equilibrium concentrations. But we don't have to determine all the Ks from experiment. We could also determine K from Appendix D data. You know, we get Appendix D data to get delta G naught at 298. Now, the easiest, I should have said there's 2. The easiest way of getting delta G naught at 298 Kelvin is by using delta G's of formation. And so the easiest way is to sum up the delta G's of formation for the products minus the sum of the delta G's of formation for the reactants. So that's probably the easiest way to get this here. The second easiest way, I think, or maybe you might argue this might be the easiest way, is to get delta H these are all at 298. I'm getting in the habit of writing the 298. Mentally, you're supposed to keep track of this in your head for all the equations, because if you start messing with the temperatures, then throw things off. So I think this is probably the second, or maybe arguably the easiest, is what we do is we calculate delta H based on delta H's of formation, so analogous equation to the delta G equation I just wrote. And we calculate delta S from the absolute entropies. So I probably think this is the easiest, or I think this is the next easiest. And so either way, you can get that. And so we can calculate K. This is very powerful because we can calculate K just from the delta G's of formation. And so we can calculate K for a large number of reactions without having to actually measure it. And the way we do that is we take advantage of the properties of logs. K is going to equal the anti-natural log E minus to the minus delta G naught at 298 over our T. T has to be at 298. And this is going to give us our K at 298. The next thing I want to do is this. While we're on this particular subject, I want to look at how temperature impacts the driving force. We know that temperature can impact the driving force. So for example, if I increase the temperature, it could potentially increase the driving force, or it could potentially decrease the driving force. And so if temperature impacts the driving force, it's also going to impact K. And so what we're going to do is we're going to do this. We're going to see how the equilibrium constant varies as a function of temperature. Do you guys remember the Clausius-Clapeyron equation, right? the Clausius-Clapeyron equation. Well, the Clausius-Clapeyron equation had a very similar form to this, right? It was an exponential function. And so what we're going to do is we're going to do this. We're going to come up with an analogous function here, and that's going to be this. We're going to take the ln of k is equal to maybe we can't do this. I'm going to be quite fancy here. I'm going to do this. I'm going to say ln of k 2 is equal to minus delta G naught, the 298 over RT 2. That's quite fancy. And then I'm going to do this. I'm going to say ln of k1 is equal to minus delta G naught. And in fact, I'm going to be a little bit lazy here. What I'm going to do is I'm going to get rid of this temperature here and just do this. And I'm going to derive an equation like Clausius-Clapeyron. I didn't derive Clausius-Clapeyron in Chem 1A, but the derivation is exactly the same as this. And so what I'm going to do is I'm going to take ln of k2 minus ln of k1. And that's going to equal minus delta G naught RT2 minus delta G naught RT1. And then I'm going to do this. I'm going to use the property of logs. I'm going to get ln of k2 over k1 is going to equal minus delta G naught minus delta G naught over RT. Oh, actually, no, I'm going to factor out the T's. It's got different expressions. Let's do this. This is going to be minus delta G naught over R times 1 over T2 minus 1 over T1. Doesn't that look like the Clausius-Clapeyron equation? Well, it is, because the equation has the same general format, and we use the same way of deriving it here. So that looks good, right? But this is totally wrong. This is a botch job. If you derive this equation like this, you just made a major screw up. Why?
Because delta G changes at different temperature.
Yeah. That's because I need to use delta G changes significantly with temperature. In fact, I can reverse the driving force with temperature, potentially, not all reactions, but some of the reactions you can actually reverse it. And so this delta G has to be at T2, and this delta G has to be at T1, right? And so even though thermodynamically this looks okay, this kind of looks okay, doesn't it? This is totally wrong. We have to be very careful, and so this is the reason I'm keeping track of everything. I'm trying to keep track of everything, standard conditions, temperature, because I don't want to screw up the equations. I mean, this does look like it would be kind of nice to do, but it's not. And so what happens if I'm not at 298 Kelvin? So let's say I want to change the driving force. I'm going to ask the same question I asked earlier. At what temperature does delta G change? So what I'm going to do here is this. Well, let me go back to the original thing before I forget to do this. Delta G at 298 at equilibrium is 0. Just know that. And so this is why I'm looking at delta G standard here. So what we're going to do is we're going to do delta G and T. Now delta G is under non-standard conditions. So if I have delta G under non-standard conditions, what is that equal to? Delta G under standard conditions plus RT ln a cube. Now I want to calculate delta G under standard conditions using the easiest method. What is the easiest method to calculate delta G under standard conditions? Yeah, the sum of the delta G's of formation of the products minus the sum of the delta G's of formation of the reactants. Can I do that here? That is, I want to do this using the easiest method. The easiest method is delta G under standard conditions is just the sum of the delta G's of the formation for the products minus the sum of the new delta G's of formation of the reactants. Can I use the easiest method here to calculate this? Yeah, I mean, this is delta G naught, this is delta G naught. So can I do that? And this equation's in the book and this equation's in the book. Can't I do that? Sure, I wanted to use the easiest method because I don't want to have to do extra work. So I'm going to try to do this using the easiest method. Will it work? Is this equation correct? Yes. Is this equation correct? Yes. Both equations are correct, so will it work?
I guess is the change for changing temperature.
The answer is no. Unfortunately, it doesn't work. And so you have to be careful. And so this is why I end up doing this. This is at delta G at temperature T. Is T at 298? No. This is a temperature not at 298. And so that means I need delta G naught at temperature T. If I use the easiest method, what am I going to get? I'm going to get delta G at, because appendix D is at 298. And delta G at 298, can I say delta G at 298 is approximately equal to delta G at temperature T? Is that valid? I did the same thing for delta H. I said delta H at 298 is about approximately equal to delta H at temperature T. I did the same thing for delta S. I said delta S at 298 is approximately equal to delta S at temperature T. Can I do the same thing for delta G? Delta G at 298 must be approximately equal to delta G at temperature T. No, because the driving force changes dramatically with temperature. And therefore, this cannot work. Shoot. So the easiest method has been eliminated. Everybody wants to do the easiest method because that's the least amount of work. How about the next easiest method? Would the next easiest method of calculating delta G under standard conditions work? Yeah. And so if we do delta G under standard conditions at temperature T, and that's going to equal delta H under standard conditions at temperature T minus T delta S under standard conditions at temperature T, we don't have the delta H and the delta S at all temperatures. We only have the delta H and the delta S at what temperature? 298, but you know, it's going to be close. A little bit of an error, but it's close enough. So we're going to just say that's going to be about equal to delta H at 298 under standard conditions minus T delta S at 298. Does this work? Yes. This works. Well, it'll be close enough. And now we could delta G at that temperature. And so what that means is this is okay. So what we'll have to do is we'll just either leave the equation like this and know that we have to calculate delta G using the next easiest method only, or some other method, but not the easiest method. And then, or we substitute. So a lot of people will substitute this. Delta G at temperature T is going to be about equal to delta H at temperature 298 minus T delta S at 298 under standard conditions. Plus RT ln of Q. And then this gets all mixed up because, hey, wait, are we under non-standard conditions? If we're under non-standard conditions, why are we using standard conditions over here? Isn't that forbidden? Because we're under non-standard conditions, how can it be allowed to use standard conditions? Yeah, so we're adding the correction to the standard conditions. So this is another point of confusion that people have, because they're thinking, oh, there's some kind of mismatch here, but it isn't a mismatch. So if we want to calculate delta G as a function of temperature under non-standard conditions, we could use this equation. All right, what if we have delta G under non-standard conditions at some temperature T, and we want to know what K is under those non-standard conditions? And so K means we must be at equilibrium. And so if we're at equilibrium, then that must mean that delta G must equal what? 0. So delta G must equal 0, which is going to equal delta H naught at 298 minus T delta S naught at 298 plus RT ln. Now ln of Q, well, Q is going to be K now. Here. And so what I'm going to do is I'm going to rearrange this. And so we'll, let's see, we'll subtract, maybe I'll subtract a minus delta H naught from both sides. And then it will go RT ln of K plus T delta S naught. And then I'm going to divide by, actually I'm going to factor out a T. Let's go ahead and factor out a T. Well, we're out of time. So I'm just, what I ultimately want to do is I want to get K as a function of temperature. So I'm going to rearrange this. I think I went the wrong direction here.
Isn't there a sign error there?
Yeah, and I probably made a sign error here. Yeah, I did make a sign error. This is minus T delta S. Right. So we'll continue this next time. We're almost done with chapter 13. We'll just look at some example calculations. But what we want to do is we want to just get the equations that we're going to use and then just apply them. I think we'll finish this on, see, Monday we're going to the computer lab, but I'll probably finish this on Monday. As a computer lab, we still don't have quite our crystals yet. We'll take a look at the crystals on Monday and then see what the progress is. I'll probably finish this on Monday and then we'll just have the test the following week. just across the hallway. We'll meet in the lab first, though, before going to the computer lab. Okay, thanks. See you tomorrow.
Thank you.
Thanks. See you. Okay. You too.